We're back with the appropriately named handout, More Differentiation. So we have four things that we're looking at here. We're getting the equations of tangents and normals. That's a core skill that you must be practiced in. You don't know what a normal is yet, but you'll know soon enough. We're looking at various notations for differentiation. That's easy and won't take long. We're looking at negative and fractional indices. It's okay, that's not very difficult. And then we're going to have a closer look at how differentiation works behind the scenes. That's pretty involved. All right, question one. So we're looking at this graph. F of x equals 0.2, etc. That's cubic, so it's going to look like that with the 3x intercepts that we know. So I've used technology to sketch that. Just to save time here. B, so that's done. B, sketch the tangents where x equals 0.5 and x equals 4. So 0.5 is like there. So we've got like a point here, and a tangent might look something like that. And x equals 4 is there, and the tangent might look something like that. All right? Naturally enough, we're going to find the gradients of those tangents. We're also going to find the equations of the tangents. We're going to sketch the normals. All right, so the normal is perpendicular to the tangent. So here's the normal at that point. Okay, and here's the normal at that point. Okay, so normal is perpendicular to the tangent at that same point. I don't like the fact that we do normals. I don't know why they're called normals. I don't know why we care about them. Whatever, we have to do them. So now we've got four lines, and we're going to find the equation of all the lines. Now, can you just rack your brain and think, how do you get the equation of a line? Well, if you have a point and a gradient, you can get the equation of the line. Well, the point is there. Point has an x value and a y value. There's an x value. How do you get the y value? Substitute it into there. Y equals f of x. So to get the y value here, substitute x equals 4 into there, all right? Okay, so a point can be done. How do we get a gradient? Well, differentiation. So f dash x will tell us the gradient of the tangent. So that'll give us the gradient of that. And then if we've got a point and a gradient, we can get the equation of the line. What about the gradient of this? Well, it's perpendicular to a gradient that we already know. So we won't be differentiating again or substituting again. We'll just be getting the negative reciprocal of a gradient we already have. All right, so let's get started. So we need to differentiate, which means we need it in expanded form. So there it is, right? You can do that, or just take my word for it. And so here's the derivative. Right, there's the derivative. Notice dealing with got a 1/5 out the front, okay, just so that I can keep this nice and tidy. I've done substitution, so for the two x values, I found the f of x value. So this here is the point, I'll use green, this here is the point half comma negative 11 over 8, right? Remember, the y value comes from f of x, right? So f of 1/2 gives me the y value. Please feel free to do that yourself and confirm. And this here is the point 4 comma negative 6 over 5, right? And then substituting into f dash x gives me the gradients of the tangents. So this one here, the gradient is 71 over 20, right? Which is like 3.55, but it's better to have fractions. Does that look like a gradient of 3.55, like across 1 up 3. See? There we go. And this one here works out to be a gradient of negative 1, right? So a nice round number. So we go across 1, down 1, right? Now my gradient's not perfectly drawn. This here is not a gradient of negative 1. It's a bit less, but whatever. Now, I've only put these in this table form for the purpose of the video. I mean, it's not a bad thing to do, but I don't want to be stopping and calculating. So we've got 4 things to find. I'm going to find the tangents first. This is exactly how I want you to set out the working. So we've got the point half, comma, negative 11 over 8. And here, so the gradient is f dash a half, which equals, right? And so here you would be pausing and calculating, right? Substitute x equals a half into there, and that equals 71 over 20. Okay, and so now we just have to find the equation of a line. That's y minus y1 equals m outside x minus x1. And we have, so x1 and y1 are the point, m is the gradient, and x and y are variables. So I'm looking like, here and here are the things that I'm substituting in. So I get y plus 11 over 8 equals, and then the gradient is 71 over 20 outside x minus a half. And then we've just got to do things to make this look like a nice equation. So I might just take a few steps and multiply it by 20 first. So I get 20y plus, and then 11 over 8 times 20 is just, 11 times 20 over 8, whatever that is. And that's 71x minus, and then 71 over 2. And now so that was like times 20. And if I multiply by 8, then I'll get 160y plus 11 times 20, which is 220, equals 71, right? 71 times 8, it should be, no, I'm not going to attempt mental arithmetic now. That's 568x minus, and then 71 over 2 times 8 is 71 times 4, so that's 284. And then to do general form, I'm just going to pop these over to the other side, and I get 568x minus 160y minus 284 minus 220 equals 0. So 568x minus 160y, and then just calculate that. Minus 504 equals 0, and then they're all even, so I'm going to divide by 2, or can I divide by 4? I think I can divide by 4. 568 divided by 4, that's 142x, and then 160 divided by 4 is 40, and then 504 divided by 4 is 504 divided by 4 is 126. We can divide even further. So that's 71x minus 20y minus 63 equals 0. Okay, for the that is the equation of that, because we use the point and the gradient, right? You can see the gradient, 71 over 20, and that point, right? And then y minus y1. Okay, so all of this was messy, but the process is simple enough. To get the equation of a line, you use the point gradient formula, and you do whatever it takes to get the information about the point and the gradient. Okay, so now the other one, so the other tangent is at 4 comma negative 6 over 5, right? The gradient is the gradient of the tangent, right? I'd like to use that notation as much as possible. The gradient of the tangent is f dash 4. You make sure you substitute into the correct thing, all right? Don't make mistakes. So f dash 4 gives us a gradient, right? I've calculated f dash 4 here to save time. But of course, in real working, you'd be pausing here and typing into your calculator. Okay, and so now y minus y1 equals m, x minus x1. So I've got y plus 6 over 5, that's my y value, is negative 1, that's my gradient of x minus 4. So this is much more civilized than before. So I get 5y plus 6, multiply everything by 5, is negative 5x plus 20. Okay, and these can go and join the other side, and we get 5x plus 5y. Then we've got a plus 6 minus 20, it's minus 14 equals 0. Right, and so that is the equation of this line. All right, done. Now I'm going to do the normals. So I need to clear some space here. Okay, so the normals. So the first one at, actually, you know what, I'm going to do the second one because I think it'd be nicer. No, I'll do the first one. Right, the first one. So I've got a half, comma, what am I doing? A half, comma, negative 11 over 8. All right, so the gradient of the normal is what? Well, it's the negative reciprocal of the gradient of the tangent. Okay? And so now I've got the point and I've got the gradient, and all I've got to do is the y minus y1 is mx minus x1. So I get y plus 11 over 8 is negative 20 over 71, x minus a half. And then we can multiply by 71, and then we can multiply by 8 and so on. Okay? I'm not going to do any more of that. It's the process that's important, not the answer. And then the other one, so 4 and negative 6 over 5, right? The gradient of the normal, right? It's a negative reciprocal of negative 1, which is positive 1. So once we know the gradient of the tangent, then we just easily get the gradient of the normal. That's the point here. Right, y minus y1 equals mx minus x1. So y plus 6 over 5 is 1 times x minus 4. So we can just get y equals x minus 4 minus 6 over 5, or y equals x minus 5 and 1/5. Okay, so that's in y equals mx plus b form rather than in general form. And if we just use a highlighter here, just to, right, this one here is this. Okay, so it's got a gradient of 1 and a y-intercept of negative 5 1/5. Right? Okay, so that's tangents and normals. Just do some practice and get the hang of it. Keep good setting out so that you don't make mistakes by substituting into the wrong thing and so on. Okay, just look at this, get the point and then an arrow and then further information and then work it out. Stick to that. Okay, question 2. Without a graph, find the equation of the tangent to that at the point 1, 5. So we don't have a graph, we don't need a graph, right? The equation of the tangent, we need a point and we need a gradient. Okay, the point is given 1, 5, and the gradient is f-1, right? Because 1 is the x value. So y equals x to the 4 minus 2x squared plus 5x plus 1. Y dash equals 4x cubed minus 4x plus 5. And at the point 1, 5, the gradient of the tangent is f dash. Now, we don't have an f, so can we write y dash evaluated when x is 1, right? And so that, let's mental calculation, we're looking here. So that's 4 minus 4 plus 5 is 5, okay? So we have y minus y1 equals x minus x1. We have y minus 5 equals 5, lots of x minus 1. I'm just going to use a bit of highlighting here. That y value is there, and that gradient value is there. It's kind of unfortunate that they're the same number, 5, right? Because it makes it look like it's meant to be when it's not, but whatever. And so we get y equals 5x minus 5 plus 5, moving the minus 5 over. So y equals 5x is the answer to this question. Okay, so I don't have a graph. I don't know what this looks like, but I do know what the equation of the tangent is at that point on the graph. This is what differentiation does for you. Very cool. Right. Question 3. Right, easier now. We're finding the first and second derivatives of the following functions using the indicated notation. Here's the indicated notation. There's a lot of different notation, right? So the differentiation here is easy, and the notation's not hard, just something for you to get used to. So if I've got f of x equals x squared plus 5, then f dash x is 2x, and f double dash x is 2. So that's the notation that we're being used to. Okay, y equals 5x cubed minus 2x squared plus 14x plus 2. Well, I get y dash is 15x squared minus 4x plus 14. And y double dash, second derivative, is 30x minus 4. Right, C, we get y equals 3.8x, that should be x to the 10, typo on my part, minus 0.5 x to the 7 plus x to the 4. Okay, so that should be x to the 10 there. And now y dash, the derivative, once again, please do not just go equals and then start differentiating, right? Y dash is 38x to the 9 minus 3.5x to the 6 plus 4x cubed. Oh, sorry, I'm supposed to use this. So the notation here is dy dx. So that is actually like the purest form of the derivative, like in terms of notation. Y dash is just a convenient abbreviation for dy dx, okay? But you'll see in a minute why that's why the dy dx form is important, and it's pronounced dy dx. The UK people pronounce it dy by dx, which is a waste of a syllable, so dy dx. Okay, and now the second derivative is a bit ungainly, d2y over dx squared. So a bit awkward. Now the second derivative, so 9 times 38, so 342, x to the 8, minus, and then that's 21x to the 5, plus 12x squared. All right, so we've got the second derivative using this notation instead of that notation. If you're wondering why so many notations, well, it's a good question. Right, now we get to x equals 3t squared minus 1. So here x is actually the dependent variable and t is the independent variable. You come across equations like this in physics kind of context, which will come up in maths as well. So x is the displacement, like how far away you are from the origin, and t is the time in seconds, for example. So now to communicate the first derivative, which would be velocity, then dx dt equals 6t. And the second derivative, which is acceleration, is 6. All right, so this could be in meters, and that's in meters per second, and that's in meters per second squared, acceleration, right? So just a quick discussion. So this is saying the derivative of x with respect to t. The with respect to means that t is the variable that we're differentiating against. So dy dx is the derivative of y with respect to x, whereas y dash is not naming the x, it's like just sort of assuming it, right? And f dash x, it's just like whatever that is, okay? And e, so another, distance time kind of equation, t to the 5 plus t squared plus t, but a different notation. So x dot is the same thing as dx dt. So that's 5t squared plus 2t plus 1, and x double dot is the same thing as the second derivative, so 10t, this was a 4, So this is 20t cubed plus 2. Okay, so the same thing throughout here. We're just taking the first and second derivative, but we're just looking at the different kinds of notation that can be used. They all have their place. So I just want to emphasize, if you say y, then that's an abbreviation for the derivative of y dash. That's the derivative of y with respect to x, and x dot is the derivative of x with respect to t. So the dot is communicating that's with respect to time. So x dash, doesn't really mean anything. Okay, you don't see that. Certainly not formally. Okay. I want to just sort of show one more example. So if I tell you the area is pi r squared, that's area of a circle, and I ask you to find dA dr, that's the derivative of a with respect to r. So it's saying that r is the variable. I mean, it's the only variable there. Pi is a constant. And then the 2 comes down and we get 2 pi r. So that's very cute. The derivative of the area is the circumference. All right, and that's not a coincidence, that's meaningful. All right, question 4. The core differentiation rule that we've used all along is this. d dx x to the n equals n x to the n minus 1. Right, so what this means, the derivative with respect to x of x to the n, and then there's the derivative. So for instance, the derivative of x to the 7 is 7x to the 6. That's the core thing that we've been using, right? But we've only used it where n is a whole number. Well, now we're going to assume, without any evidence, that this rule applies to negative and fractional indices, right? And it does, thankfully, and find the derivative of the following. So a, y equals square root of x. Well, we can write that as x to the half. And now we can differentiate it as half x. Now, what happens when you subtract 1 from half? You get negative a half, right? And then we'll just write that to look a little bit nicer. That's a half times 1 over root x. And so y dash is 1 over 2 root x. Okay, so y equals root x gives you y dash is 1 over 2 root x. That's a nice thing to maybe keep in mind, right? Okay, b. So we've got y equals cube root of x. Well, that can be written y equals x to the 1/3. So y dash is 1/3 x, and then we've got to subtract 1 from a third. We get negative 2/3. So that's y dash is 1/3 times 1 over, x to the 2/3, or y dash is 1 over 3 times the square root of, the cube root of x squared. Now, this here is a bit, a bit ungainly, so I just leave the answer like that. All right, so I've made a different aesthetic decision here compared to here. That's because square root's just more common, and this is a nice form, all right? Okay, but the point is we can do the differentiation using fractional indices. C, y equals 1 over x. That can be rewritten as y equals x to the negative 1. So y dash is negative 1 times x to the negative 2, right? Or negative 1 over x squared. There's the derivative of y equals x to the negative 1. I want to point out to you, if you graph y equals 1 over x, then that always, every single tangent you can draw has a negative gradient, every single one. And look at this expression. That's always negative because x squared is always positive, and so the negative means that this whole thing is always negative, so it fits. As x gets large, the gradient sort of really flattens out. Well, here, as x gets large, this y dash approaches 0. And as x gets really small, close to 0, then the gradient gets close to vertical. Well, when x is a really small number here, then y dash is a really huge number. right? If you subbed in x equals 1 over 1,000, that's really, really close to 0, then you'd end up with y dash equals negative 1,000,000, right? That's really steep, isn't it? Okay, D. Y equals 1 over x to the 6. Well, that can be written as y equals x to the negative 6. So y dash is negative 6 times x to the negative 7. So that's negative 6 over x to the 7. Okay, so I won't bother drawing a graph and all that, but that's easy to obtain. E, y equals the fifth root of x to the 7. That can be written as y equals x to the 7 over 5. So y dash is 7/5 times x to the 2/5. Okay, I'm not going to put that in surd form. And F, y equals 1 over 4th root of x cubed. That can be written as y equals x to the negative 3 over 4. So y dash is negative 3/4 x to the negative 7 over 4. And there we go. Right, so that is applying, that's doing, there are plenty of textbook questions. I think there's a whole exercise basically about this kind of thing. Question 6, perform a complete differentiation by first principles. So in class, I skipped over, I discussed that but didn't write a full answer, and I skipped that one entirely. This is going to get pretty involved. I'm just going to pause and take a drink of water. Okay, just want to say first off, if you don't get this, that's okay. You can completely ignore it if you want. Very unlikely to be asked in an exam to do a differentiation by first principles. And if you are, you can just say, oh, you know what, I might just go and get some other marks instead. Okay, that's up to you. But of course, I'm going to teach it thoroughly. The motivation for teaching it thoroughly is so that we understand that when we have y equals, for instance, x to the power of 6, and we differentiate that to y equals 6x to the 5, like we're not just pushing ink around the page, we have some understanding of like why that's true. All right, so watch and learn. Right, now before I start any of this, I'm drawing a diagram. So I have a function, and I want to know that didn't work. I want to know the equation of a tangent, right? But the problem is I only know, not the equation, I want to know the gradient of a tangent, but the gradient is y2 minus y1 over x2 minus x1. There's no other way to find a gradient than that. So what we do is we say, right, what if I get that point and one other, and now I can find a gradient, and that's an approximation of that. Problem is it's a bad approximation. So instead, like, I'll get a different point, right? Like a closer point, and then find that gradient. That's a better approximation, right? But the closer I get, the better, but it'll never be exactly the same. But what we hope is that if we look at a few of these gradients, right, then we can hopefully see that they seem to be approaching some number. So if we found that the first one was a gradient of, let's say, 4.15, and then the second one was 4.05, and then the third one was 4.005, and then we did another one and we got 4.0005, like we might speculate that if we keep getting closer and closer, then it's really just getting closer and closer to 4, and then we could just call this a gradient of 4 and be done with it, right? Now, that's what we do, but we do it mathematically so that we know that it's approaching 4 and not just in our imagination. Okay, so fresh diagram to start the theory. Okay, so here's our thingo. Right, I'm going to say here's a point we're interested in, right? And I'm going to call it x, right? And then the second point that we choose, and to make this thing, which is called a secant, or it's really called a chord. It's only a secant if you extend it according to the Cambridge textbook, but it doesn't matter. We want to know the gradient of the secant, right? Now, that, I'm not going to call this position y or q or whatever. I'm going to call it x plus delta x. So delta x just means a small value of x. And what we really want is for it to be a lot smaller than this. We want it to be like that, or even small. We want it to be infinitesimally small. We want to consider like, okay, so the gradient is equal to m, which is a function of delta x. Like the value of delta x you choose was going to determine what the gradient is. Is it going to be like that, or is it going to be like that, or like that, or like that, or, right? Different choices of delta x are going to give you a different gradient. And so we're going to ask what happens to the gradient as delta x approaches 0. Okay, so what we need here is we need some points, right? So that here is the point x comma f of x. And this point here is x plus delta x, that's the x value, and the y value is f of x plus delta x, right? And so we can have like a triangle here, and the rise is the difference in y values. So that's f of x plus delta x minus f of x. And the run is simply delta x. Okay, so the way this is constructed is we choose what the run is and then we find out what the rise is, right? But we're allowing this to be variable. And by the way, delta x is like a single symbol. So when I write something like delta x squared, I don't mean delta times x squared, I mean delta x squared, okay? All right, so that's our important diagram. And I'm just going to remove all of this. And I'm going to move all of this. Right. In fact, I think I'll shrink it as well. Okay, and so the gradient of the secant m as a function of delta x is simply y2 minus y, or the rise over the run, right? So I get f of x plus delta x minus f of x over delta x. Okay, that's going to be my starting point for each of these things. Not a fresh diagram each time. This is my starting point, right? And you should understand it. It's simply two y values subtracted divided by the run. All right, so for question A, right? So we've got f of x equals x squared. So the gradient as a function of delta x is, what's this? This is x plus delta x all squared minus x squared over delta x. Okay, you just take a moment to understand that if you substitute x, like f of x equals x squared in here, then f of x plus delta x is x plus delta x squared, right? So that's that minus f of x over delta x. Okay, but now I can actually do some mathematics with this, right? So the denominator won't change, but this is x squared plus 2x delta x plus delta x squared minus x squared. Okay, so I've expanded the perfect square. And now I've got x squared minus x squared, right? So they cancel each other out. And then we're going to look at this, right? We get some cancellation here. And I want to point out that like, oh man, I really want to know what happens when delta x approaches 0, but unfortunately we've got delta x in the denominator, so I guess I'll never know. But now, look at this. We've got 2x delta x plus delta x squared over delta x. That is 2x plus delta x. That simplifies to that. There's no more fraction, no more denominator, right? And so as delta x approaches 0, you can see that the gradient of the secant approaches 2x, because that approaches 0, so it's like vanishing. And so what we're left with is 2x. So if this was like a value of 7, then that gradient is like a value of, is 2 times 7 is 14, right? So therefore, the derivative of x squared is 2x, which we knew, but now have proved it, right? So there you go. There's our first differentiation by first principles. Okay, I'm going to keep that there, and I'm going to do the cubed one now. So say f of x equals x cubed. And so the gradient as a function of delta x is, right, I've got a fraction with delta x in the denominator. This is x plus delta x all cubed minus x cubed, right? So that is this using f of x equals x cubed. Okay, now we know how to expand a cube. We get x cubed plus 3x delta x, 3x squared delta x plus 3x delta x plus delta x cubed, and then minus x cubed. So you can see that has expanded to that, right? Pascal's triangle, that sort of thing. All right, as before, they cancel. And as before, we can divide through by delta x. So we get 3x squared, and then that delta x cancels, plus 3, there should be a squared there, okay? So the ascending powers, so delta x squared, delta x cubed, right? This is 3x delta x plus delta x squared, right? So this is a bit more complicated than what we had here. All right, now, but there's no more fraction. There's no more denominator. And now I can say as delta x approaches 0, right, I can note that 3x delta x approaches 0 and delta x squared approaches 0. And so what we have is the gradient approaches 3x squared. See? That approaches 0. That approaches 0. This doesn't. That doesn't have a delta x in it, so this approaching 0 has no effect on that. And so what we have is that the derivative, the gradient function of x cubed, is 3x squared, right? As we already knew, but now we really know. All right? It's a beautiful thing. I talked a little bit about x to the n in class. I'm not going to repeat that here. For one thing, I'm running out of battery. But it's just like a bigger expansion than that, right? X squared plus 6x. Look, I think I won't do it here. I'll just tell you why I included it, right? We know that the derivative of that should be 2x plus 6. And when we do all this work, we see that it is, right? We see that it really is that. So it's just a bigger expansion, okay? So you could try that yourself if you want to. I think with the amount of battery I've got left, I've got to choose one of these two. I think I'll do this one, right? It's really interesting. And it's interesting because the mathematics of it plays out so differently compared to what we've seen with x squared and x cubed. Okay, so for g, we've got f of x equals square root of x. And so the gradient of that, right, so if I apply f of x equals that, then I get the square root of x plus delta x minus the square root of x over delta x. Okay, now this is really different from before. I don't get any like cancellation like that, so it's like harder. What can I do here? And certainly no way can I cancel that with that. That's inside a square root. So what can I do here? Well, what I can do is I can multiply by the following thing. Square root of x plus delta x plus square root of x over the same thing. Okay, so this is just 1, so I'm just multiplying by 1, but now I get to use difference of two squares. That times that is a difference of two squares, which means I'll get to like not have these square roots anymore. Now let me do the denominator first. So that is okay, there's no simplification in the denominator, right? So that looks really concerning. Now let's look at the numerator. Well, I get one thing squared minus the other thing squared. So I get x plus delta x minus x. And now I do get a cancellation, and you can see that we're left with just that, and that's going to cancel with that. And so I get 1 over the square root of x plus delta x plus delta x, right? Plus square root of x, right? Okay, so that is my gradient function, right? What that means is, here's what square root of x looks like. And if I chose x equals 7 and 9, right, and I wanted to know what the gradient of that secant is, then I can plug in x equals 7 and delta x equals 2, right? And basically I get 1 over the square root of 9 plus the square root of 7. So that's 1 over 3 plus root 7. Now, you could work that out, exactly what that secant is, and find that it's that using y2 minus y1, etc. But I just found it very easily using this, because all of this hard work's been done. Anyway, back to what we were talking about. So, bye-bye, and see you later. Okay, as delta x approaches 0, what does this approach? Well, we can see that the square root of x plus delta x just approaches the square root of x. And so what we have is m of delta x, the gradient of the secant, approaches 1 over square root of x plus square root of x, which is 1 over 2 root x. And so therefore, the derivative with respect to x of the square root of x is equal to 1 over 2 root x. And that is what we found back here. Okay, so there you go. It's a freaking miracle. All right, it's very interesting mathematics, and I hope you enjoyed it. If you'd like to try 1 over x, then you're most welcome to. And if you struggle, you can ask me about it later. Okay, so there's another video to come, but I just want to point out that the textbook, we've sort of done everything from 804 to 806 here. The first principle stuff is earlier in the chapter, but I want you to forget about that. For practicing basic differentiation and differentiation with negative and fractional indices and finding tangents and normals, like you just to look at these, right? Don't think that you have to do every question. Just do a broad sample of them. You can always go back and do more later. You want to practice as many different skills as you can. Okay, see you in the next video.